to study the electronic configuration. What is electronic configuration? The electronic configuration of an atom is the distribution of electrons in various shells or subshells around the nucleus of an atom. As we know that the electron orbits or shells in an atom are represented the capital letters K, L, M, N, O, P, etc. This is how the orbits or the shells in an atom are represented. These different shells K, L, M, N corresponds to the value of the principal quantum number N equal to 1, 2, 3, 4, 5, 6, 7, etc. respectively. For the orbit for which N is equal to 1 is represented by capital K. The orbit for which the present quantum number N is equal to 2 is denoted by L. N is equal to 3 is represented by M, 4 is represented by N, and so on. So, these are the principal quantum numbers of the total quantum numbers, and these quantum numbers, these shells are represented by the capital letters K, L, M, N, O, P, etc. However, these shells are further divided into the subshells. These shells are further divided into subshells. The electrons having the same orbital quantum number L form the subshell. Subshells, and these different subshells are represented by the letters S, P, D, M, Z, H, etc. So these small letters are used to represent the subshells. These subshells correspond to a particular value of the angular momentum quantum number. As we know that the orbital quantum number L is found to have the values starting from 0, and the maximum value of L is equal to n minus 1. So the first subshell for which L is equal to 0 is represented by the letter S. The second subshell corresponding to L is equal to 1 is represented by letter small p. The subshell having L is equal to 2 is represented by D. And the subshell having L is equal to 3 is represented by F, and so on. So, the different subshells having the values of L equal to 0, 1, 2, 3, 4, 5, 6, etc. are respectively represented by the letters S, P, D, M, G, H, etc. So these are the letters used to represent the different shells and the different subshells in an atom. Now, if we consider the value of L is equal to 0, say for L is equal to 0, we get Ls subshell, or L is equal to 0, we have S subshell. for L is equal to 2, we have D subset. For L equal to 3, we have F subset, and so on. So, for different values of L, the different subsets are respectively represented by the letters S, P, D, F, etc. Now, these letters S, P, D, F has a certain historical reference. These letters S, P, D, F have certain historical reference. The letter S indicates the sharp series. The letter P corresponds to the principal series. The letter D corresponds to diffuse series. And the letter F corresponds to fundamental series. So these different subsets, the letters used are S, P, D, F, and these S, P, D, F are going to have certain historical reference, and the historical reference is S stands for sharp series, P stands for principal series, D stands for diffuse series, and F stands for fundamental series. Then, for K shape, let us see the K shape. We know that for K shell, the value of principal quantum number n is equal to 1, and that of orbital quantum number 6 is equal to 0, because the values of n start from 0 and proceed up to n minus 1. So that for n is equal to 1, the value of n, possible value of n is only 0. Now, if we have these values of n and l, then what will be the values of another two quantum numbers? We know that in vector atom model, the 4 quantum numbers are used. The first is the principal quantum number, second is orbital quantum number, third is orbital magnetic quantum number, and the fourth is spin magnetic quantum number. The third quantum number is ml, and this ml is how to vary between minus l to plus. So since here the value of l is 0, the value of ml for K shell works out to be equal to 0 is. And the values of ms, the spin magnetic quantum number, as we know well, are going to have only 2 possible values, and those 2 possible values are plus half and minus half. These are only 2 possible values of ms. So, with these values of the 4 quantum numbers n, l, ml, and ms, what will be the possible number of sets of these 4 quantum numbers? The first possible set of these 4 quantum numbers is n equal to 1, l equal to 0, ml is equal to 0, and ms equal to plus half. So this is the first possible set of all the 4 quantum numbers, and the second possible set of these 4 quantum numbers is n equal to 1, l equal to 0, ml equal to 0, and ms equal to minus. Can it be possible for us to write down the third possible set for all these 4 quantum numbers for these values of n, l, ml and ms? So there is no possible third set is not possible. So for in Cation, so what we can conclude here is that in Cation the maximum number of electrons that can be accommodated is equal to 2. So that is how no third set is possible, and according to this is in accordance with the Pauli's exclusion principle, and the case set can have only 2 electrons, and this is in accordance with the Pauli's exclusion principle. In accordance with the Pauli's exclusion principle, we have seen that the maximum number of electrons that can be accommodated in a particular shell is given by twice n square, and since here n is equal to 1, this is equal to 2. If we substitute n is equal to 1, 1 square is 1 and 2 into 1 is 2 itself. So the maximum number of electrons that can be accommodated in the Cation is going to be equal to 2. Similarly, we can proceed to obtain the maximum number of electrons that can be accommodated in the different shells such as L, M, N, O, P, etc. So in practice, we understand that the electronic structure of a complex atom is filled in succession of the field levels increasing in the energy. The order of filling of the subshells in an atom is found to be like this. When a particular subshell is filled, the next electron goes into the lowest energy vacant subshell. The next electron is going to go into the next vacant subshell. So that when a subshell is filled, the next electron goes into the lowest possible energy vacant subshell, and maximum 2 electrons can be accommodated in a particular subshell. The state of electron in the given orbital is specified by the 3 quantum numbers n, l and m, and out of the 2 electrons in an orbital, 1 electron has the spin magnetic quantum number ms is equal to plus half, and the other electron has the spin orbital magnetic quantum number ms is equal to minus half. So this ms is equal to plus half indicates the spin up state, and ms equal to minus half indicates that the spin vector is pointing in the downward direction, that is spin downside. So depending on what is the value of ms, this spin moment vector is either directed in the upward direction or is going to be directed in the downward direction, and that is called as spin up state and spin down state. Okay. So the number of orbitals in a given subshell is found to be equal to twice L plus 1. The number of orbitals in a given subshell is found to be twice L plus 1. Thus, S subshell L is equal to 0 has only 1 orbital. For S subshell, there is only one orbital. For P subshell, for which L is equal to 1, there are 3 orbitals. For D subshell, for which L is equal to 2, has 5 orbitals, and so on. So, for the filling of electrons into the subshells, in addition to the Pauli's exclusion principle, Hund's rule is also obeyed. Now, what is this Hund's rule? This Hund's rule states that when an atom has orbital of equal energy, the order in which they are filled with the electrons is such that a maximum number of electrons have unpaired space. The maximum number of electrons will have unpaired space. So, both this exclusion principle and the Hund's rule can be understood with the help of this examples. So, let us illustrate how this electron distribution takes place in an atom. And while discussing this, it is understood that how both the Pauli's exclusion principle and the Hund's rule are. So, for example, the first example we consider here is that of hydrogen. For hydrogen, we know that Z is equal to 1. The atomic number of hydrogen is 1, which indicates that there is only one electron in hydrogen atom. And this electron, both electron in hydrogen atom, will enter into 1s subshell of K. This lone electron in hydrogen atom will take the place in K shell of 1s subshell. 1s subshell of K shell. Then, if we consider the second example, that of helium, we know that for helium, Z is equal to 2, and these 2 electrons in helium atom will occupy the places in 1s subshell of K shell itself. Both these electrons in helium atom will be accommodated in 1s subshell of the K shell, because the maximum number of electrons that can be accommodated in the S subshell is 2. Then the third atom is lithium, for which the atomic number is 3, and out of these 3 electrons of lithium atom, 2 electrons will be accommodated in 1s level, and the third electron will be accommodated in the 2s level. So, the electronic configuration for lithium will be 1s2, 2s1. So, that is how these 3 electrons of lithium will be distributed. Then for beryllium, Z is equal to 4, and the electronic configuration beryllium will be 1s2, 2s2. Then for boron, the atomic number Z is 5 and the electronic configuration will be 1s2, 2s2 and 2p1. So next higher level will be then for carbon, Z is equal to 6 and the electron configuration will be 1s2, 2s2 and 2p. So like that, the different electrons in the different atoms will be accommodated in the different subshells of the different shells. So here in this case we observe that there are two 2p electrons. There are two 2p electrons. So these two 2p electrons will enter into these 2p electrons will enter into the different shells, different subshells that we'll see little later on. But before that, what we shall try to understand here is the table given here. This K level for which L is equal to 1, L is 0 and subshell is denoted by 1s and the number of electrons in this subshell, the maximum number of electrons accommodated in this subshell is 2. So that in the K shell, the maximum number of electrons accommodated is equal to 2. Then the second shell or orbit is denoted by L, for which the principal quantum number n is 2, so that the possible values of L are 0 and 1. The first subshell for which L is equal to 0 is denoted by 2s and the second subshell for which L is equal to 1 is denoted by 2p. This first subshell 2s will accommodate maximum 2 electrons and the 2p subshell can accommodate maximum 6 electrons, so that the total number of electrons that can be accommodated in L level or L shell will be equal to 8. Then the next shell is N shell, for which the principal quantum number n is equal to 3. If n is equal to 3, L can take the values 0, 1, 2, etc. 0, 1, 2 only, etc. The sub-level corresponding to L is equal to 0 is denoted by 3s. The sub-level corresponding to L is equal to 1 is represented by 3p, and the sub-level corresponding to L is equal to 2 is denoted by 3p. This sub-level 3s can accommodate maximum 2 electrons, 3p level can accommodate maximum 6 electrons, and 3d level can accommodate maximum 10 electrons, such that the total number of electrons that can be accommodated in n shell or in the third orbit is equal to 80. So like that, the fourth shell is denoted by n shell, for which the principal quantum number n is equal to 4, and if n is equal to 4, the possible values of L are 0, 1, 2, 3. This sub-level corresponding to L is equal to 0 is denoted by 4s. The sub-level corresponding to L is equal to 1 is denoted by 4p. Then the sub-level corresponding to L is equal to 2 is denoted by 4d, and the sub-level corresponding to L is equal to 3 is denoted by 4l. The maximum number of electrons that can be accommodated in 4s level is 2, that in 4p level is 6, in 4d level is 10, and the level 4f can accommodate maximum 14 electrons. So that in the fourth orbit, that is in level n, the maximum number of electrons that can be accommodated is equal to 30. So this table summarizes how the different electrons can be accommodated in the different levels or sub-levels. So and while filling up these electrons in the different orbitals, we were discussing this table. So with this electronic configuration, now we'll see how these levels will be filled for the different shells and subshells. So here we have shell and subshell. First we have K shell, subshell is 1s, then we have 2s, then we have L shell, here we have 1s, 2 electrons, 2s, 2 electrons, then 2p, these are 2p. Then the atoms. Here we consider the atom for which Z is equal to 4 is beryllium. The 4 electrons in this beryllium atom are distributed. The first 2 electrons are accommodated in K shell, that is in 1s level, and the remaining 2 electrons are accommodated in 2s level. This is Z is equal to 4. Then next is Z is equal to 5. Boron. Out of the 5 electrons of boron atom, first 2 electrons will occupy the places in 1s level. Then next 2 electrons will occupy the place in 2s level, and then the 5th electron will occupy the place in 2b level. Then for Z is equal to 6, carbon, we have the distribution. Out of these 6 electrons of carbon, the first 2 electrons will be accommodated in 1s subshell. Next 2 electrons will be accommodated in 2s subshell, and the remaining 2 electrons will not enter into the first 2p level, but these 2 electrons will enter into the separate 2p levels. They will enter into the separate 2p levels. Then for Z is equal to 7, nitrogen, the electronic rate distribution will be like this. Out of these 7 electrons, the first 2 electrons will be accommodated in 1s level, next 2 electrons will be accommodated in 2s level, and the remaining 3 electrons will occupy the places in the 2p level separately. These electrons will not be paired here. These electrons will not be paired here. This is in accordance with the Hund's law. This is in accordance with the Hund's law. So the maximum number of electrons will try to remain unpaired. The maximum number of electrons will try to remain unpaired. So next is Z is equal to 8. Z is equal to 8 is oxygen, and for oxygen the 8 electrons will be out of these 8 electrons, the 2 electrons will be accommodated in 1s level, the 2 electrons will be accommodated in 2s level, sub level. Then first 3 electrons will occupy the places, 3 separate places in 2p level, but one more electron remains here, and that electron then gets paired with the first sub level in 2p state, 2p sub level. Then for Z is equal to 9, the 2 electrons are accommodated in 1s level, 2 electrons are accommodated in 2s level, and 1 electron each are accommodated first in 2p level, and still there are 2 electrons are left over. So these 2 electrons then gets paired with the first 2p sublevels. So like that, the maximum number of subshells try to remain unpaired. So this is in accordance with the Hund's law. So that is how the electron distribution can take place, and we can write the electron configuration. For beryllium it will be 1s2, 2s2. For boron it will be 1s2, 2s2, 2p1. For carbon it will be 1s2, 2s2 and 2p2. For nitrogen it will be 1s2, 2s2, 2p3. For oxygen it will be 1s2, 2s2 and 2p4. And for Z is equal to 9, it will be 1s2, 2s2 and 2p7. So like that, the electrons are distributed in the atoms in the higher and higher orbitals and sub-levels. So that is about this electronic configuration, and next we want to study the quantum states of an electron. That will continue in the next video. Okay. Thank you.